concept of entropy is going to be discussed in this lecture. So we'll be covering this presentation over next 1 hour. And then from 4 to 5 p.m., we will study the topic of noiseless channel encoding. Okay, so in today's talk, we'll be having multiple different sections. One is the generation of information. The other is biases theorem, conditional entropy, and information transfer. These are basically the three main topics. And it kind of will kind of continue from what we had discussed in yesterday's lecture, uh, where we said that a general model of information transfer, a general communication system, can be represented in the manner shown here. So there is some information source that selects one out of some capital M messages, correct? So, I mean, I don't know how you want to look at it, but suppose you are writing some essay or story or paragraph or an email. What you do is you pick up your pen, you take a paper, or nowadays maybe you start typing on your iPad screen or your computer screen, and the act of typing right away forces you to select, correct? So there are 26 letters of English alphabet if you are writing in English. In any other language, similarly, there will be some discrete set of alphabetic letters, and you select one letter out of all the multiple possibilities. And in a fundamental sense, that act of selection generates information. And that selection happens at an atomic level, at every letter that you select, but it is hierarchical in nature, right? So you not only select a letter, but that letter is part of a sequence that we call word. So you select words actually out of multiple different words that are possible. And then through the words, you construct a sentence. So you are selecting a sentence out of multiple possibilities. And eventually your goal is that whichever entity you selected, maybe a letter or a word or a sentence or a paragraph or a chapter or entire story, that is one out of multiple possibilities that you selected. And your goal is that whoever is the receiver, the destination of your information, when they receive that message, they end up selecting the same exact message that you selected. Although you are not physically co-located, or maybe it might be that you are transmitting information in time. You write something today with the intention that maybe your children or your grandchildren will read you later. So you are sending the information in time. Either way, either you are transmitting information at a given time across spatially separated source and destination, or it could be in addition separated in time as well. But the goal is that at the destination, by receiving your message, the receiver will end up selecting this. Ideally, it will end up selecting the same message that you selected, correct? And that is how the communication happens. When the message that you want to convey gets transmitted accurately, the yellow circle that I have drawn here matches the yellow circle at the destination site. Otherwise, you might select the second yellow circle, but the destination might end up selecting the last circle, and then we will say that the communication is erroneous. What you intended to convey was not the message that got received. So that is the overall intent of any communication system. And see that this is something that we all can understand very well, because here the exact same thing applies to human communication without any electronic devices involved in between. But today's electronic devices also operate along the same principle that I have outlined here on this slide. What they do is that they'll take the selected message, maybe the email that you're typing, that email will go to a communication transmitter, and somehow that message will get converted to a physical signal. It typically is in the form of an electromagnetic wave, but it doesn't have to be. It could be any type of physical signal that can be transmitted over a communication channel. The communication channel invariably introduces certain noise, and then the receiver gets a noisy replica of the signal, and hopefully the receiver is not overwhelmed with the noise so that it can still uh, get the same message that was transmitted. And in this context, the the parameter that is of importance is this capital K, and that K is the source alphabet, right? So for example, when we were discussing the model for transmitting binary information through this coronavirus disease estimation problem, the source is binary, capital K is equal to 2, and the uh, one of the two symbols gets transmitted whether there is disease or not, no disease. As I said, if you're using an English keyboard, then you will have access to maybe 128 such characters, which are the ASCII character set, so on and so forth. And we'll say that these individual symbols occur with certain probabilities, and they may or may not be all the same. So, no, I'm in an online session, uh, so basically there'll be some probability distribution over this capital K different symbols. In coronavirus problem that we discussed yesterday, we saw that bit 0 was happening with 99% probability, and bit 1, meaning that somebody has a disease, has this disease, was having probability of 0.01, 1%. If it was English characters, then we know that letters such as A, E, I, O, U, the vowels happen with far greater probabilities than some other English alphabetic letters such as Z or Q or J, etc. But regardless, each symbol will have certain probability, and we require that the sum of this probability is equal to 1. Okay, so the question is, what is the information generated when the source emits kth symbol D of k with probability P of k? And the information theoretic answer is the one that I'll give you. But I wanted to just ask you whether you have any thoughts on this. So yesterday we discussed the same type of question. How do you define the information? How would you measure it, etc.? And the answer that some of you had expressed, that the message should be unknown at the receiver, right? So that part plays a major role in this definition. The unknown part of the message being transmitted is represented by this probability P of k. If P of k is 1, then it means that the receiver knows exactly this letter or this symbol is going to occur with 100% certainty. Likewise, if P of k is 0, then also there is no point of conveying any information to the receiver because the receiver already knows about it. Right? We talked about uh, that the sun will rise tomorrow in the sky. P of k is 1 there. Or if you say that, I don't know, the moon will become full moon within next 15 days or next 1 month. Again, P of k is 1. And then there will be negation of such true statements for which P of k is 0. And those statements won't convey much information. So somehow, one answer to this question is that information should be roughly inversely proportional to P of k. So the greater the P of k, meaning more certain we are in terms of its probability of occurrence, less information we get. Does that make sense? Yes, no? Okay, good. So at least one person is answering. Yeah, so basically I of k should be inversely proportional to P of k. The other part is a little more, we'll need little more thought on this. But what information theory says is that I of k should be logarithmically related to P of k. Any idea why that would be the case? Why would logarithm enter the picture? So yesterday we considered one question, that the question of how many binary strings there are of length 100 bits. And what was the answer that we got? Yesterday we already looked at this answer. 2 to the power 100, correct. Uh, yeah, yeah, please be more interactive so I know that all of you are awake. Um, right, so if there are 100 bits and all of these bits are equally likely, then there can be 2 to the power 100 different binary strings. So now 2 to the power 100 is a big number. So let us say that uh, maybe we are just looking at, let's say, 4 bits, right? So with 4 bits, how many different binary strings can we have? Suppose we are having only 4 bits. Correct. So, sorry, I had a phone call. I had to take it. So sorry for the interrupt. So exactly correct. I see a lot of responses. So if there are 4 bits, we can have 16 different binary strings of length 4 bits. So look at those numbers. How are they related? The data size is 4, but the number of possibilities is exponential function of 4. It is 2 to the power 4. Uh, Let's put it other way, that we we talked about this information source having certain set of alphabets, D1 to D of K. Suppose capital K is 16, meaning that total different possibilities that you have that you are selecting from. Remember, we have this diagram set of messages. So suppose there are 16 such messages, D1, D2 up to D of K. And let us say that all of them occur with equal probability. So this P of K will be obviously 1 over 16, correct? Now, in this case, suppose if I select one out of the 16 symbols, all of them are occurring with the same probability. What is the size of data that I will generate? We just answered that question. It is 4 bits, right? Because total number of symbols is 16. All of them are occurring with the same probability. And so I can represent the first symbol as 4 zeros, second as 0001, 0010, all the way to 1111. 16 and 4, how are they related? Logarithmically, correct? Log base 2 of 16 is 4. So that is the general answer to this question of how to define information, how to measure it, how to quantify it. Furthermore, here in this example, what is 16? We said that there are 16 different symbols and each of them are occurring with the same probability of 1 over 16. So P of K is 1 over 16 for all different symbols. If I want a formula to convert P of K to I of K, then I have all the answers that I need. First of all, I said that information should be inversely proportional to P of K. P of K is 1 over 16. Inverse of 1 over 16 is 16. And then I said that information should be a logarithmic function. So if I take log base 2 of 16, I get 4. And 4 is the size of the data that gets generated when I pick one of those 16 symbols. That is the argument. Who gets it? Did I make myself clear or did I go too fast? Not clear. What part is not clear? See, the first part is that I of K should be inversely proportional to P of K. Is that part clear? The greater the certainty of a particular symbol or a message, lesser the information that gets generated when that message or that symbol occurs. That part is clear? Okay. So if that is clear, then the second part is that in this example that I was taking, suppose the entire set of messages has 16 different symbols. Maybe it's some strange type of alphabet similar to English alphabet, where instead of 26 letters, they have only 16 letters. And also, unlike English, maybe all of those letters occur with the same probability. And because we said that the sum of the probability has to be 1, it means that each of that symbol occurs with a probability of 1 over 16. P of K is 1 over 16. But we know that because I am considering a set of 16 symbols, when I pick any one of them, I will need 4 bits. So the way to relate P of k, which is 1 over 16, to the size of the data that gets generated when I select one particular symbol, which is 4, is through logarithm. Logarithm of 1 over P of k is 4. Okay, so that is the content of this slide. That whose final answer is that information generated when the kth symbol occurs is defined as log base 2 of 1 over P of k, or alternatively negative log base 2 of P of k. This is a very fundamental formula that you should keep in mind, because this is the bedrock of classical information theory. And when you go on to study quantum information theory, you can contrast the definition of information in the quantum world against the definition of information in the classical world. Okay? I hope that you understand this part. If not, I have written down what I just talked about in these two slides. You can review it on your own. But the point is that I of k is negative log base 2 of P of k. P of k is the probability of the occurrence of the kth symbol. And we have already talked about this probability mass function. All of these different symbols have different probabilities. Their sum has to be equal to 1, etc. So I won't get into these details of random variable and cumulative mass function. But what then we will look at is, fine, individually, each letter of this informative source generates certain information I of k, negative log base 2 of P of k. But what about the information generated uh, by the entire source? How to quantify the informativeness of the whole source taken as an aggregate? And there the information theory says that we should take expected value of I of k, where I of k is treated as a random variable. Okay? And the answer that we get when we take expectation of I of k is called entropy, h of x. And entropy is the fundamental quantity that characterizes whether a source is informative or non-informative. Okay? It is not the individual occurrences of the symbols that say whether the source is informative or not. It is the overall or the average information generated by the source, which is the entropy. So because I of k is negative log base 2 of P of k, and the way we take expectation is we take the random variable, multiply by P of k. The formula for entropy is the one that I am highlighting here. Okay, so this is a basic concept of information theory. Entropy is negative of summation over product of P of k and logarithm of P of k. Okay, so let us look at one example now. In this example, we are considering a Bernoulli variable, which is essentially a binary variable. It takes two values, 0 and 1. And as a variable, we have this parameter q, which characterizes whether 1 is more likely or 0 is more likely. Right? When q is 0.5, they both are equally likely. It represents the outcome of the toss of a coin in a mathematical sense. But in terms of the real world events, it represents all sorts of different things. You can call X to represent the answer to the question of whether it will snow. in Gandhinagar, or whether it will rain in Gandhinagar tomorrow, or at any other city. Or you can call X as India is playing against Australia in one day international, whether India will win. X equal to 1 means India wins, X equal to 0 means India doesn't win. And each of these two possibilities have certain probabilities assigned to it. Um, some, so in some uh, case, let's say uh, the parents are expecting a child and they want to know whether it's going to be boy or a girl, and they have a certain probability in mind. Let's say x equal to 0 means boy, x equal to 1 means girl. So if q is 0.5, then they attribute equal probability of their child being a boy versus a girl. So x represents a wide variety of different events of real life. And for this x, the information for these two symbols is negative log base 2 of q, negative log base 2 of 1 minus q. And entropy is given by this formula that I am highlighting here. Now let us look at what happens when q varies from 0 to 1, or here I change the notations. Instead of calling it q, I'm calling it p. P varies from 0 to 1. What is p? Probability that x is equal to 1. So what we see is that when x is the probability that x is equal to 1 is when it is either 0 or when it is 1. In either of these two cases, the source ceases to be informative source. It doesn't remain informative. Why? Because the y-axis, which is the entropy, falls down to 0. Only when there is certain randomness, an element of surprise, an element of unknownness in the occurrences of symbol, which happens when I move p away from 0 or from 1, then the informativeness of the source in terms of entropy goes up, climbs up, and it attains the maximum value when p is equal to 0.5. So what we are saying is that when these two events are equally likely, that is when the source is most informative in the average sense. Individually, the messages might convey a lot of information. For example, when p is 0.99, p is 0.001, meaning that that particular event is going to occur with a very small chance. As we saw earlier, when that event actually occurs, negative log base 2 of p of k becomes a very large number, and a lot of information gets generated. Anytime and every time such rare events happen, our newspapers get filled with the news of that event. The headline is made up of all the things related to that event, right? Um, I'll give you a very recent example. Uh, you may know that uh, an Hindi movie actor who is very well known, Dharmendra, he passed away uh, last month. And you know that when he passed away, there was a lot of news headlines that was generated. Why? Because the passing away of Dharmendra is a very rare event. It happened only one time in his lifetime and in all of our lifetimes. Right? So when it actually happened, that rare event, because corresponding P was very small, it ended up generating a lot of information. But still, if you ask the overall informativeness of the source, then that source overall has very little information. What do I mean by that? The question in this case becomes whether Dharmendra is alive or whether he is no longer alive. That is the question. Its answer equal to 1 means he is alive. Its answer equal to 0 means he is not alive. The answer became 0 once in his entire lifetime. And so it's a very rare event. Its probability was very tiny, minuscule. And so when that event happened, a lot of information got generated, as we all noticed. But the overall informativeness of the whole source, which is x equal to 0 and x equal to 1, is very small because most of the time x was 0. In fact, all the time x was 0 until the day he passed. And so over his entire lifetime, we never heard any news related to that particular question because it was not informative. And so the entropy of that source is very small. Most of the time, you don't need to put any number of bits. On the other hand, when India is playing against Australia, and let's say both are equal in terms of competence, both these teams, then we have fundamental uncertainty. P is equal to nearly 0.5. We don't know whether India is going to win or Australia is going to win. And so that is why we are glued to the TV set, because the maximum information is generated by the outcome of that match. Okay, so that is, I think, the main theoretical concept that I wish to convey to you. I hope that at least some of it has come across. This is all in the classical sense, where bits take only two values, zeros, 0 versus 1. And in this case, the information in the average sense is defined by the concept of entropy. Okay. Looking back at the example that I was giving you, where there were 4 symbols and each of the symbols had equal probability of 1 over 16. What do you think the entropy would be in that case? H of x defined here. For the case when capital K is 16, P of K is 1 over 16. What will be entropy, H of x? Any thought? When capital K is 16 and P of K is 1 over 16, what is H of x, entropy of x? That is the question. Why would it be 0? My question is that I gave you another previously an example where capital K was 16. There were 16 different symbols. Each of the symbols was occurring with a probability of, with equal probability. So P of K was 1 over 16 for all of the symbols. Given that, what is the entropy for that source? Somebody did give the right answer that it is, but okay, log base 1 is equal to 0, but where are we having 1 here? There is no 1 in this formula. P of k is 1 over 16, not 1. So somebody gave the right answer that it will be 16. Why 16? Because log base 2 of P of k is going to be 4. Negative log base 2 of P of k. I of k is going to be 4. 4 uh, is the common value across all 16 symbols, so I can pull it out. Then what remains is just summation of P of k, but that equals 1. And so therefore the answer is 4. And that actually makes, hopefully it makes intuitive sense. We have 16 different symbols to transmit. Obviously we need 4 bits. And so in this particular case, the definition of entropy agrees with our notion about how much information would get generated when we have that particular source. Okay, I'll skip over some of these slides for the sake of time. Let me go to the next topic, which is biases theorem. I'm sure that all of you would have had some exposure to biases theorem, either in your high school or in your college, etc. Basically, it's a theorem which has become very prominent, and it has it is driving a lot of development and research, not only in communication theory but also in many other aspects, signal processing, ML, etc. The reason is because our human brains also are quite adept at doing what biases theorem says. And the reason our brains have become adept at performing this mathematics of bias theorem is possibly because our brains have evolved to be intelligent in the real world scenarios. And all the real world scenarios can be cast in this framework that I had shown you yesterday. There is a world of causes and there is a world of effects. We have access only to this world of effects, or what we call evidence. And once we measure a particular outcome, when we have certain evidence, our goal is to go back and see which of the two possible causes in this case is more likely than the other. So we already talked about this coronavirus disease, but the same formulation applies to many different cases. Suppose you wake up one day and you have some pain. Your immediate concern is whether you will have cavity in your tooth. The question of whether there is cavity in the tooth belongs to the world of causes. Pain is what you have measured. It belongs to the world of effect or evidence. When you measure a particular outcome, your immediate goal is to go back and see whether one cause is more likely than the other. You want to know whether it's more likely that you have cavity versus less likely that you have cavity. Suppose you buy some fancy car and you're sleeping in your bedroom at night and suddenly the car alarm goes up at 3 o'clock in the morning. You hear the car alarm, and that again belongs to the world of effects. It's an evidence, an outcome. And so your immediate concern is the world of causes. Which of the two causes is more likely? Are the burglars attempting to steal my car, or maybe the car alarm went off because it's very sensitive and maybe some cat jumped over my car? Right? So there are so many such different scenarios. Even let's say selection of a player in some sports activity. One player is favored by one coach and the other player is favored by, let's say, the captain. And so now when you see a particular player included in the team, then you want to know whether that player got selected because the coach or because of the captain, etc. Always we look at the outcome in the real world and then immediately we go back and try to assess which of the possible causes are more likely. If you have one outcome, then suddenly one particular cause becomes more likely than the other. If you have another outcome, then the other cause becomes more likely than the first one, right? We all know this by heart. The way I'm drawing it might confuse you, but it's nothing new to us. Our brains are so adept at doing this that we take it for granted. In the laboratory test experiment that I was describing, you go and do the test, and if the test result comes out negative, t is equal to 0, you are happy because you immediately conclude that c equal to 0 is more likely than c equal to 1. On the other hand, if the test result comes out positive, then you start perspiring, your heart rate goes up, you have a lot of worry because you think that maybe c equal to 1 now is more likely than c equal to 0, right? So this is something that we are all very much familiar with. This is not something that anybody needs to be taught. It's kind of ingrained in our psychology. The mathematics of bias's theorem is something that our brain does all the time. But when we want to make a computer do what our brain does, that is where the life becomes difficult, because we sometimes don't know what our brains are doing. Our brains, the operation of our brains is to a large extent a mystery. Except maybe for the biases theorem, the formulas have been laid out. I will let you look at the formula, and you can work through the formulas to evaluate the conditional probabilities, right? So in the example that we gave yesterday, uh, the prior probabilities of X, whether you have the disease or you don't have the disease, were given by these numbers. This was the general prevalence of, let's say, coronavirus in the population. 1% of the people have the disease, 99% people don't have the disease. So that is the prior distribution of X. We were also given what is known as likelihood function, that if somebody has the disease, they go and take the test, the probability that the test outcome will be 1, it will become positive, is 95%. But there is 5% chance of misdetection. X is equal to 1, but Y still comes out as negative. The test equipment is faulty with a chance of 5%. Same way, if somebody does not have the disease, sometimes there will be a false alarm. The Y output, the test result will become 1 even when X is equal to 0. And that, we called it the probability of false alarm, and that was 5%. And the probability of the test outcome becoming negative when the person actually doesn't have disease was 95% in the problem that we looked at yesterday. The question is that the patient takes the test and the result comes out positive. What are the chances that X is equal to 1? Y equal to 1 is given. That fellow is looking at his laboratory test report and it says that the test is positive. The question is, what are the chances that that person actually has the disease? And so that is where this biases rule comes into play. This is the formula of biases rule. This is the likelihood function. This is the prior. And the denominator is called evidence. Sometimes evidence is not explicitly calculated. You just denote 1 divided by probability of Y equal to 1 as some variable alpha. The likelihood and the priors are given. So you say that the probability that X is equal to 1 given Y equal to 1 is simply this quantity. Same way, you will need to evaluate the chances that the person does not have the disease when the test came out positive. And so again, plugging in the number, This alpha variable remains the same in both the cases, and you get this answer. And now what you do is you say that summation of the probabilities have to be equal to 1, which means that alpha will have to be equal to this quantity. And once we put in that value of alpha, then we get the answer that probability of x equal to 1 given y equal to 1 is 0.16, and x equal to 0 given y equal to 1 is 0.84. So this answer is little surprising, that even when the test came out positive, the chance that the person has the disease is only 16%. What is alpha? Alpha is a normalizing constant. It's basically denoting inverse of the probability of the evidence. In this case, the evidence is equal to 1. The test came out positive. What is the probability that the test will come out positive? That is 1 over alpha. How do we compute that probability of 1 over alpha? Through this math. And then we get the particular value of alpha. So you see that I didn't get the question. There was some question about safe exposure limit. I don't know the answer to that. I'll just move on. Now, the last thing in this particular topic that I want to mention is the idea of conditional entropy and the concept of information transfer over a noisy channel. If you recall, yesterday we asked this question that suppose the information gets generated at the source, but it gets transmitted over a channel which is inherently noisy. Then how much of the information would actually get through? And there we considered the notion of influence. How much of the belief at the receiver gets modified by the receipt of this noisy output of communication channel? So there, what information theory says, and this is a little advanced topic, but it's a topic that is needed to fully appreciate the breadth and the width of the information theory. This is the topic that actually drives that equation we were looking at yesterday. Remember, R is less than or equal to W times log base 2 of 1 plus PS over Pn. That equation came about because of these notions of conditional entropy and information transfer. The way to motivate this topic is to again go back to this particular situation. See, when you don't have any measurement, right, then all you know is the prior. If you don't have any symptoms and it's life as usual, and then if somebody asks you, what are the chances that you have coronavirus disease? Then you'll say, I don't know, I will just guess that the chances are 0.01 because that is the prior. That an average person picked at random has C equal to 1 with a probability of 0.01. So that is one variable. That is called unconditional variable, unconditional C or unconditional X, where we are not looking at any evidence, we are not looking at any test equipment or test apparatus at all. And for that variable, we have already defined the concept of information, that is the entropy that we just defined. But you see, something interesting happens. when you go and take the test. If the test comes out negative, then this variable kind of transforms itself. First, you thought that you have maybe 1% chance of having the disease because roughly that is the prior probability. But you just want to feel more assured, and so you go and take the test comes out negative. So now that 1% became maybe 0.0001%. You became exceedingly sure that you don't have the disease because test came out negative. So 99% and 1% changed to 99.999% and 0.001%. The degree of belief became more stronger in some sense. On the other hand, you went and took the test came out positive, t was equal to 1. We just looked at the math. Now that 99% and 1% changed to 84% and 16%. You see the difference? In one case, t equal to 0, you are relieved. You can say with utmost confidence, maybe not 100% confidence, but still a lot of confidence that you don't have the disease. So you go back home happy. On the other case, you are worried because now the probability has gone up. Before it was 1%, now it became 16%. So there are three different quantities or three different scenarios of the same variable C. And so what conditional entropy does is it evaluates the entropy for each possible scenarios. So conditional entropy of x given y equal to j is simply expected value of ik given y equal to j. Basically, when y is equal to 0, that source behaves in a certain manner, 99.999% versus 0.001%. What is the entropy of that source? Versus suppose y is equal to 1, now it behaves like 84% and 16%. So what is the entropy of that source? So you have two different conditional entropies. Entropy of x given y equal to 0, entropy of x given y equal to 1. And then overall conditional entropy is obtained by averaging over all values of y. So y equal to 0, y equal to 1, you evaluate the conditional entropy and then you average. You take expectation of that. And so you get this long formula. This becomes the overall conditional entropy. Entropy of x given y. And then finally, the information transfer is defined at the unconditional entropy, the entropy of the source before you took any test or before you performed any measurement. That is the original entropy at h of x unconditional entropy minus the conditional entropy, entropy of x given y. The difference is the amount of information that got through. If you think of entropy of x as in some sense, defining the temperature of the source, when entropy is high, it means there's a lot of vibration, lot of randomness, lot of uncertainty. And then entropy of x given y as the temperature of the source after you make the measurement. The information transfer is the quantity that equals the amount by which the temperature of the source reduced after measuring a particular outcome. So if the temperature of the source doesn't reduce at all, then it means that you didn't get any information. If the temperature of the source reduced and became 0, then it means that you got the maximum amount of information. So that is the notion of IXY, information transfer from X to Y. And that kind of completes this initial introduction to the main concepts of information theory. The entropy, which is the entropy of the original source, irrespective of the noisy transmissions. and IXY, how much information actually goes through a noisy channel, which is the difference between the unconditional entropy and the conditional entropy, and that is the rate of information transfer. These are the two main concepts. Okay, so with that, I'll conclude this lecture. You can ask questions if you have any.
You can post the questions. We can take a 5 minutes break.
Hmm.
In meanwhile, you can post your questions. Once we resume the next session, we can take those questions.
Okay, so we'll take about 5 minutes break.
Yes.
So, Professor Rajendra,
Yes.
uh, how shall I send the soft copies, the PDF files of these lectures? Should I just email it to you?
Yeah, you can email to me. I will post them on the canvas.
Um, okay, so
I will post them on the LMS which we are using, which is Canvas, where the participants would be able to see it. You can send me through by email, or you can share it through your Google Drive also. Everything is fine.
So there is this fdp.eict@mnit.ac.in. I reply to that email. That is fine.
Uh, no, reply to my email
Reply
because
to.
I will not be able to access that. That is for technical staff, so you can send it to me. I will post it on Canvas.
Okay, fine.
So, can we begin the next session?
Sure.
All right. So there is one question which is what is the range of entropy? I think that's the question which was posted.
Yeah. Okay. So uh, the range of entropy goes from zero, which is when if you have, let's say, a source with k different symbols, k different messages, and if any one of those messages has a probability of either one or zero, then the entropy becomes zero. Well, actually, if any one of the messages has probability of one, which means that all the other messages need to have probability of zero. In that case, the entropy becomes zero because now you know everything that is to know about that source. Um, that is the lowest value of entropy. The highest value of entropy occurs when all of those k symbols are equally likely. And then the entropy becomes simply logarithm base 2 of capital K, number of messages. So in the example that we were taking, capital K was 16. We were saying that all of those 16 messages are equally likely, and therefore the entropy was 4 bits. If you have 128 symbols, if they are all equally likely, then the entropy is 7 bits. In the example that we considered yesterday, there were 2 to the power 100 different symbols. Remember, we said that that number is so large that it is 4 times greater than the age of universe in picoseconds. If all of those messages are equally likely, then the entropy of that source would be 100 bits. Okay, so that is how we define the maximum value of the entropy of any source. Okay, so if there are no further questions, can I start this next?
Yeah. There are no further questions.
So I'm sharing my screen.
There is one question which is posted just now. How can Bayes rules be used to estimate cancer risk in progeny given cancer history in previous generations?
Sorry, I. Okay. So I think it's a good question. So the cancer history in previous generations would become the prior that we were talking about, right? Let us do an equivalence with the example that we have already studied, the coronavirus detection problem. In that case, the prior we took it as 1%, meaning that 1% of the general population has the disease, 99% of the people don't have the disease. So in your case, let's say that the prior generations, the cancer history was 1%, meaning that 1% of the ancestors um, had this particular disease, 99% of the ancestors don't have the disease. So that becomes prior, x equal to 0, x equal to 1, right? X equal to 0 means you don't have the disease, x equal to 1 means you have the disease. Now, one day you wake up and you say that I'm worried about the possibility that you have the disease. And so you go and do a laboratory test. Now, suppose the test comes out positive. Let's say that that it's a mammogram test. Let's say some lady, some female goes and does that test for breast cancer detection. And the mammogram tests are, as far as I know, I'm not a doctor, but the little that I know is that mammogram tests are not 100% reliable, right? So sometimes when the person doesn't have disease, they will wrongly flag it as t equal to 1. And sometimes when the person has the disease, they will wrongly miss it. They will call it t equal to 0. So now suppose somebody went and did the mammogram and the test came out positive, t equal to 1. Now that lady is really worried and she's asking fundamentally this question, what are the chances that I have the disease? If we say that mammogram tests are reliable with 95% accuracy and they make error with 5% chance, and that error is both the ways. When the disease is not present, the test will come out positive. That is one type of error. When the disease is present, the test will come out negative. That is another type of error. The probability of both those errors is 5%. Those were the two red arrows that in that bias chart that I was showing you. If both are 5%, t equals 1, prior is 1%, then that female still doesn't have too much of a reason to worry because the probability that she has the disease is still only 16%. There is still 84% chance that she actually doesn't have the disease. But that is because prior is very small. your ancestors have not a, there are not too many incidences of cancer in your ancestry tree. But if suppose that changed, suppose if prior became 50%, means half of the ancestors had the disease and other half didn't have the disease, then things are very different. If that in that case, if this particular female goes and takes the test, it comes out positive, then there is 95% chance that she has the disease, not 16% anymore. Right? So prior plays a very important role. I hope that explains to some extent the answer to your question. Okay. So then let us begin this next topic of noiseless channel coding. Okay, um, so let us see. In the classical world, it is extremely important to encode the information in an efficient manner. I cannot overemphasize the importance of this. I don't even have to emphasize the importance of this because you know this very well, right? When you're using cell phones and you're taking photos and videos and you're downloading all the other types of information, you know that the memory becomes full. And so next time you purchase the cell phone, you pay extra money to buy a device which has larger memory. Or maybe you subscribe to all this Google or Microsoft subscriptions, which gives you certain amount of memory, maybe, I don't know, 1 TB or something. But then you pay on a monthly basis. Uh, how much memory is used by the information that you generate and that you consume? That is the topic of this particular lecture. And we want the representation of information to be as efficient as possible. Again, that is very easily understood today because the money that we pay to Microsoft for buying their subscription, right, is the money that goes out of our pocket. Nothing could be more um, understandable than that. And it's not at an individual level, it's also think about the amount of data that YouTube or Instagram and Facebook, etc., they have to store on a daily basis. There, you know that all these big companies have big data sets, huge farms where they the entire acres and acres are taken up not by nothing other than just data storage servers, where all the videos and etc. they are kept. So again, there, if you can figure out a way to represent all this data in an efficient manner, then uh, obviously you are solving a big problem. So that is the topic of this particular lecture, how to represent the information in an efficient manner, where we discard the effect of noise. It's a noiseless mechanism of coding the information. Okay, so that is the discussion that we'll do over next 1 hour or so. By the way, tomorrow we will look at the counterpart of this topic, which is coding in the presence of noise. Okay. So this slide shows an end-to-end diagram of a digital communication system. And by that, I mean everything and anything that we all are using on a day-to-day basis, whether it is cell phone, whether it is internet, whether it is satellite phones, uh, anything, right? Whenever we use, let's say, a digital TV, maybe Tata Sky or something like that, Ultimately, there is a source, a transmitter, and then there is a receiver. And in the previous lecture, we looked at a very basic diagram of the communication that happens between the transmitter and the receiver. This is more of an engineering diagram. That diagram was more of an abstract concept diagram. This is an engineering diagram. All of these devices ultimately can be cast in terms of this diagram, whether it is your cell phone or whether it is your Tata Sky receiver, etc. What they do is they possibly take an analog source, maybe the output of some camera or something, and then there's some quantization that happens to convert analog to digital. If the source is already digital, then this A to D converter is bypassed and the generated information is directly sent to the source encoder. The output of encoder is given to encryption to preserve the secrecy of the message. Then it goes to channel encoder, modulator, and then finally modulator output is transmitted over a communication channel. The output of channel is sent to the receiver, which will have the inverse functions, demodulator, decoder, decryption, so on and so forth. So when we talk about noiseless channel coding, essentially we are considering source encoding and source decoding. Think of source encoding as data compression. When you, let's say, use WinZip or WinRAR, you have some bunch of data and then you compress it using that utility, that tool. So that operation would be called encoding of the original informative source. And let's say now somebody sends you that zip file and you click on it and you unzip it. That is the source decoding. Okay, so that is basically what we are going to talk about. But we are not going to talk about it in terms of zip files and all that. Although that is ultimately what it boils down to. But instead, we are going to look at the concept behind this these functions. Okay, so I'll skip over some of the slides and just look at what do we mean by data compression. So a lot of the digital data contains redundant information, right? So what do I mean by redundancy? One very good example is, maybe let me stop sharing my screen. You just look at my video that now I have been able to activate. So what do you see, right? You see me, hopefully, if my video is coming through. The part which is changing is practically just my face. The rest of my body remains the same. The background remains the same. Okay, nothing there changes as you receive one video frame after another video frame after another video frame. So there is a lot of redundancy in the video stream that I am transmitting and you are receiving. And that is the occasion, that is the reason why data compression is possible. What a smart device does is, after I turn on my video, that smart data compressor will see that, okay, this fellow is just projecting his portrait, where just middle part of the screen has little bit of change from one moment to another. But if you look at all the other side or background, it's remaining exactly the same. If it is remaining exactly the same, why do I need to transmit all that information as video? I can just transmit one photo, get it across to the receiver, ask the receiver to keep it constant. And then on that constant background, I will just keep on changing the part of the original video that is changing, right? So I did data compression. I became more efficient in the way that I am representing information. Does it make sense? The example that I gave, was it something that you could understand? Okay, fine. Looks like um, there's some lag in your response. So basically, the purpose is to squeeze out the redundant information as much as possible. And the question then becomes, what are the good algorithms that allow us to do that? And what is the maximum possible data compression that we can achieve, provided that we want to recover the exact original information once we decompress the data. So these are some of the questions. The importance of this problem, as I said, it cannot be overstated. I can talk about it for hours and hours, why this is a very important problem. Now, in order to understand this particular topic in a mathematical conceptual sense, what we'll do is we'll consider this uh, notion of discrete memoryless source, DMS. So discrete means that it's an alphabetic uh, source of information. Information generated is already digitized. So that is the discrete part of DMS. Memoryless means it's basically random. One letter has no connection to the other letter. So a monkey which is punching the keys of a typewriter is a DMS. Whereas if you or I compose a song or a play, then we wouldn't be called DMS because we are not typing on the keyboard in a completely random manner. So we will be considering actually the DMS. And you might wonder that, but that is not reality, right? A lot of the informative sources have memory in them. The reason we'll consider DMS is because it will give us the concept. And then later on, we can generalize. In terms of concept, the DMS is a powerful uh, entity that allows us to get to the heart of the source coding problem. Okay, so what is source coding? Source code is a rule which maps symbols to a sequence of bits. Okay, so let's say you have four symbols, x1, x2, x3, x4. Maybe let's say they are A, B, C, D, or different colors, red, blue, green. This should have been x3, sorry, there is a typo here. And that's a purple or something, right? So you have four different symbols. If it is a fixed length encoding, then you take each symbol and map it to the same number of bits. So here we are mapping it to 2 bits. And so because there are four symbols, we give them these 2 bits that are shown here. A variable length code, in contrast, maps the source symbols into code words of different length. So x1 is 1, x2 could be 0, 1, then 1, 0, 1, and then 1, 1. So they are fundamentally two different ways of encoding the, the symbols. Right? And this encoding is typically binary because our computers understand the binary language. Now my question is, why would anybody want to do variable length coding when fixed length looks kind of easy and simple? Why to introduce this more complicated way of encoding using variable lengths? To avoid redundancy, sort of, yeah, but why? I mean, why would variable length avoid redundancy? Why would fixed length not also avoid redundancy? To save memory, but again, the same question, why would fixed length use more memory than variable length? To reduce number of switching in the bits. Why would we want to reduce the number of switching in the bits? Low power. I mean, this is right now, we are not talking about the power at all. This is all representation of symbols into bits. This is all in the logical sense. There is no physical signal that we are even looking at. So we can't define the notion of a power, notion of the power. We will do that when we study the topic of modulation. That is when bits will get mapped to actual physical physical signals, electromagnetic waves. So exactly, this is the right answer. Frequently used symbols will have shorter lengths. That is the right answer. Frequently used symbols should have shorter lengths. And that, I think, as somebody else said, will save us memory. Okay, so look at that. Frequently used symbols should have shorter length. What does it mean? Frequently used means P of K. The probability of the occurrence of those symbols is high. So letters E or I or O, these letters have high probability. And so actually in the representation, A, E, I, these letters should be given smaller length. But remember we said information is inversely proportional to P of K. Somehow that connects here. The intuitive notion that you had is exactly represented mathematically by the definition of I of K that we looked at in the previous lecture. I of K is log base 2 of 1 over P of K. So correct. Variable length coding becomes useful because the symbols will not have the same probability of occurrences. And so we want to be able to use less number of bits for the symbols that are more likely and larger number of bits. In this case, x3 has 101 because x3 is not as probable as x1. So we can understand why variable length coding would be preferred over fixed length coding. Fixed length coding is, by the way, the right thing to do when all the symbols are equally likely. And variable length is the right thing to do when different symbols have different probability of occurrence. Now, if you look at almost all the informative sources, the probability of occurrences of the symbols that they generate are not going to be the same. And so the variable length coding is more likely to be the right way to proceed. Now, as we consider variable length coding, right away we are confronted with a problem. It could be that we end up assigning bits to the symbols, which makes the overall encoded string to be very confusing. So let us look at this particular example. X1 is assigned bit 1, X2 0 0, X3 0 1, and X4 1 0. Okay, so let's say we did this assignment. The problem happens when we get some string like 001, 001 at the receiver. There are two perfectly correct ways to decode this string. One is X2, which is 00. So there's 00, we'll call it X2. Then the next one is 1, so we'll call it X1. And then 00, X2, and then again X1. So that is one completely legitimate way. But I could also call it uh, hidden X2, which is 00, and then X4, which is 10, and then X2 again, which is 01. So you see that there are two different but correct ways of decoding. Which one is the right one? We don't know. The decoder has fundamental ambiguity. And that is happening because this is not a uniquely decodable code. Okay, so that is the thing that we should always try to avoid, because otherwise we'll get into trouble at the receiver. The reason why it is not uniquely decodable is X1 is a prefix of X4. Right? X1 is 1 and X4 is 10. So you see that X4 is X1 followed by another bit 0. Whenever that happens, when one symbol becomes a prefix of another symbol, then it becomes not a uniquely decodable code. On the other hand, this particular assignment is uniquely decodable because no string is a prefix of another string. You can check. A way to look at this is maybe through a binary tree. So the first example that we had here, X1 is 000, X2 is 0010, so on and so forth, is represented here through a binary tree. For a code to be uniquely decodable, we said that a particular symbol should not ever be a prefix of another symbol, which means that if I put a particular symbol on this tree by this red circle, then I should not have any other red circle as I traverse from the root to the leaf. You will see that X3 doesn't have any red circle sitting on top of it. X4, X5, X6, X7, they are all independent in this. There are no prefixes. On the other hand, if I consider this problematic code on a binary tree, we will right away see the problem that happens. X1 and X2 are fine, but look at X4 and X3. X3 became prefix of X4. Basically, X3 is the parent, X4 is the child. For a uniquely decodable code, that should never happen. One assigned node should never be the parent or the grandparent, etc., of a child node. So this is the problematic code compared to the code on the previous slide. So we'll look at some notations so that we can formulate this method properly. So n max is going to be the length of the longest code. So what is n max here? And what is n max here? Come on, this is easy. N max is 3. N max is the length of the longest code word. What is n max here? Why is nobody answering? This is the easiest ones. Why do you say 3 and 5 and you're missing the right answer? Look at the, yeah, it is 4. Length of the longest code word. Here it is obviously 4, right? What is n max here? Obviously it is. I mean, look at, there are 4 code words. What is the length of the longest code word? 2, correct. N max is basically the number of levels of this binary tree. How many levels do we have? Not counting the root. So here there are 1, 2, 3, and 4, 4 levels. Here there are 2 levels. So n max represents uh, the size of the tree in some sense. Now we will define the subtree under an assigned code to have certain number of leaves, and that number of leaf has to be 2 to the power n max minus n of l. What do I mean by that? Let's look at a of l for this x of 3, a of 3 for this x of 3. How many leaf nodes there are that are under this x of 3? 1, 2, 3, 4, right? What is 2 to the power n max minus n of 3? N of 3 is 2, n max is 4. 2 to the power 4 minus 2 is 2 to the power 2, which is 4. That is equal to this number. Got it? What is going to be a of 1? Who can tell me that? Did you understand the question? What is a of 1? Meaning that, how did you define a of 1, a of 2, a of 3? We defined it as the number of leaf nodes underneath a particular symbol. And we defined it as 2 to the power n max minus n of l. So if you look at x of 3, what are the number of leaf nodes underneath x of 3? If you look at this subtree that belongs to x of 3, there are 4 leaf nodes. So the answer a of 3, the answer to the question of what is a of 3 is 4. Why 4? One way is to just look at how many leaf nodes there are under x of 3. The other way is to say that a of 3 is going to be 2 to the power n max minus n of 3. N of 3 is 2 because x3 has 2 bits. N max we said is 4. So n max minus n of 2 is n of 3 is 2. So basically 2 to the power 2 is this 4 bit. 4. What about n of 1? That is my question. What is the subtree that, yeah, 2 is the right answer, correct. Look at the subtree that belongs to x of 1. That subtree is the one that I'm covering through my cursor. How many leaf nodes does it have? 2. So a of 1 is 2. What about a of 2? A of 2 is already a leaf node. So you count that, and so a of 2 becomes 1. A of 3 is 4. A of 4 is 4. A of 5 is 1. A of 6 is 1. And a of 7 is again 2. I hope that you got this. Just to test, what is going to be a of 3? 2, correct. Not 4. Why do you say 4? We look at x of 3, look at the subtree underneath x of 3. How many leaf nodes does it have? 2. So a of 3 is 2. A of 1, A of 2, and A of 4 is 1 because they themselves are leaf nodes. Basically, we are counting the number of leaf nodes that are underneath each symbol. Now, there is a very important mathematical theorem. It's called Kraft's inequality. It says that for prefix-free code, where individual code words have length of n of l, and n of l varies from 1 bit uh, to the maximum number of bits, this equality always holds. Summation of 2 to the power minus nl, L going from 1 to capital L, capital L is the number of symbols, is always going to be equal to or less than 1. Okay, so how to prove this theorem? The subtree under an assigned code word of length n of l bits has a of l 2 to the power n max minus n of l leaf nodes. We saw this just now. Because we are saying that this is a prefix-free code, all of the subtrees are disjoint, meaning that they don't overlap with each other. That is the definition of the assignment being prefix-free. Finally, the total number of leaf nodes is equal to 2 to the power n max. And so therefore, summation of a of l has to be less than or equal to 2 to the power n max because a of l counts the leaf nodes. These leaf nodes are mutually exclusive. They form mutually exclusive sets. And so when I add them up, that sum can never exceed 2 to the power n max, which is the total number of leaf nodes. But a of l, we said it is equal to 2 to the power n max minus nl. So summation of 2 to the power n max minus nl over l can never exceed 2 to the power n max if it is a prefix-free code. Now, if I cancel 2 to the power n max from both the sides of this inequality, I get the Kraft's inequality. Okay, this is a fundamental result of um, noiseless channel encoding. What is N of L? It is the length of the encoding that we do for the L symbol. Now, suppose that for some code, the Kraft's inequality turns into an equality, meaning that summation of 2 to the power minus NL over L becomes equal to 1. Suppose if this ends up happening, what does this remind you right away? Which is the other thing that we have seen where if you have L different numbers, they add up to 1. Those numbers are, if you have collection of L numbers and if they add up to 1, then those numbers would be, one good way to consider that set of numbers would be to say that they are what is q? 1 over q, but what is q? In this case, we can possibly consider the left side of inequality as forming a probability mass function. Because if all of these numbers are probabilities, then they add up to 1. And so now, if I actually make a leap of faith and equate 2 to the power minus NL as some type of probability of the L symbol, then N of L becomes negative log base 2 of P of L, P hat of L. But you see, this is exactly the definition of the information that we just looked at in the previous lecture. So somehow Kraft's inequality that applies to prefix-free variable length code is leading us to the same answer that we derived on the previous lecture from a purely conceptual sense. Basically, the length of encoding of a symbol coming out of an informative source is turning out to be equal to the notion of information content of that particular symbol. So here is one more question. I hope that a lot of you are responsive. What will be expected value of N of L, or the average value of N of L? Considering what we studied in the previous lecture. If I want to know what is the average number of length, what is the average length of encodings, the bit encodings that I apply to different information symbols, given this, what I have written here, what will be that average number equivalent to? Come on, somebody has to say something. I don't, I don't know how, I don't know how many attendees are here, but it seems like very quiet to me. Nobody is responding. Have I already lost all of you? Or you have been listening to me? -1. Why would it be -1? Thank you. Thank you for responding. Yes. What is expectation of N of L? Remember, we looked at two different concepts last in the last lecture. One was information content of a source, which we called I of k. And what was the other related concept that we considered? We said that that is the fundamental measure of the information content of a source. Okay, never mind. I'll move forward. The average number of bits, exactly, entropy is the right answer. So the average number of bits that we would need to represent the output of the source, which is given by this formula. This is the very well-known expression of how you take average. You multiply the random variable, which is n of k in this case, with the probability of that symbol, kth symbol, and then you get the average. The goal of the source encoding is to obviously minimize this average. And the strategy is to assign short code words to the symbols that are more likely. And the fundamental theory of information in communication is that for a uniquely decodable source code, the output can be recovered without any uh, errors. This rate is lower bounded by entropy. Okay, the rate that we define here, it can be never less than entropy, meaning that you can try to compress the output of an informative source. You will never be able to compress it below entropy. Entropy is the fundamental limit to which we can compress. If we try to compress beyond that, then we won't be able to recover the original uh, information accurately. This is the source coding theorem or data compression theorem. How to prove the theorem? Let's not worry about it as of now. Maybe I'll conclude today's lecture with two examples of how to do source coding. This is again in the classical sense. If you have binary data, or rather, if you have some informative source which is generating uh, some symbols that would typically not be binary, the Huffman encoding and the Lempel-Ziv coding, they try to do optimal encoding of these sources. Huffman coding requires the knowledge of the probabilities of the symbols. Lempel-Ziv coding operates in a blind manner. It doesn't require the probabilities to be known. There are many other algorithms, Shannon-Fano, Shannon-Fano-Elias, arithmetic coding, etc., that are used for the same purpose. And today there are even more advanced algorithms. Many of them are based on artificial intelligence, etc., that are used for the source encoding. But in the context of this course, they are out of scope. What does Huffman coding do? Huffman encoder operates in a very simple manner. It first of all takes all the symbols and orders them in the descending order of probability. It makes a table where the um, most frequent symbol is listed at the top, followed by the uh, less frequent symbol, so on and so forth. Uh, then what it does is it takes the two lowest probability symbols and combines them into a pseudo symbol. And then it keeps on repeating on the step one and step two until only one single combined symbol remains. And through that, it forms a binary tree, and then it just goes down the binary tree to assign the bit sequences for each symbol. Let us look at an example of that. Suppose I have 6 symbols and their probabilities are listed in the second column. I've already ordered them in the descending order of their probabilities. And so in the first step, Huffman encoder will take X5 and X6 and use them to make this pseudo symbol. And obviously its probability will be sum of these two probabilities, 0.12. Once you do that, now you have another table. X5 and X6 are consumed or subsumed under this star symbol. And so Now, instead of 6 symbols, I have 5 symbols. I will do again the ordering so that they are in descending order. And yeah, so now this is the first step. That step is represented here. And then the next symbol was x4.1, so that comes here. So now I combine these 2 symbols to make another symbol which is having an accumulated probability of 0.22. Basically, I keep on doing that. Now I have this shortened table, ordered in descending order. So zero point 0.2, 0.30, they became the smallest probability symbols. I combine them to make a pseudo symbol. Its probability is 0.33. This part of the tree uh, is the one that we already had on the previous slide. And so now I have even smaller table. I again do the same step. Eventually, I'm left with a final tree which looks like this. And now I just go down this binary tree. Whenever I go rightward, I put a 0. Whenever I go leftward, I put a 1. And that way, I form this encoding uh, table. So there are 2 things to be noticed. X1, which has the largest probability, it automatically got assigned the smallest code word. X5 and X6, which had the lowest probability, they automatically got assigned the largest, the longest code, which is what we want. The second thing that Huffman coding does naturally is that it's a prefix-free code. You will not find one symbol sitting on top of another symbol. Okay? And we can do some calculation. We can calculate the entropy of the source, and we can also calculate the rate of this Huffman encoding. And you see that rate is 2.2, entropy is 2.18. The rate came out to be very close to entropy, but it is not less than entropy. It cannot be less than entropy. Okay, so that is the idea behind Huffman and Lempensive coding is a blind scheme where basically there is some parsing that happens, and based on the parsing, the algorithm constructs some dictionary. I won't get into this too much because this is a little bit of an advanced topic. I don't believe that it will have any relevance to the overall subject of quantum information that you are studying. But if you're interested, you can either look at the slides or you can do your own study on lamp-pencil coding. Okay, I think I'll conclude here. I have one more section in terms of how, remember I said that uh, the rate of an encoding of a source can be made arbitrarily close to, but not less than the entropy of the source. This is a fundamental theorem of information theory. How to prove this theorem? That is, the proof part is here that makes use of the binomial random variable. This is actually that, remember yesterday we looked at this question of inspecting some bicycles. So the proof actually makes use of this. And that is what I was telling you yesterday, that um, the initial foundations of the information theory uh, is by analyzing this type of problems. But given the shortage of time, I won't get into the proof at this time. Um, I think in context of quantum information theory, I think it is actually useful for you to understand the proof of this source coding theorem, but maybe uh, given the lack of time, I will skip that at this time. Okay,
All
so
right.
that is all from my side.
Okay, thank you once again. So we'll continue with the rest of the topics related to the fundamentals of digital communication tomorrow again at 3 p.m. The WebEx link will remain same as you have used today. And so we meet tomorrow. Thank you very much.
Okay. Thank you. Bye. Bye.
Bye.